All right. Couple things. This upcoming weekend, there will be a midterm exam. It'll be similar in nature to how the quizzes have gone. You'll take it on your own. You'll have more time, obviously, it'll be longer, but still the same sort of idea. I will get some practice materials posted up by tomorrow. The midterm will cover material through today. So we'll have class today. Homework is due on Wednesday, I believe, for this I/J material. And then that'll be all the content that will be on the midterm. The practice materials I posted might have some other stuff on them. I will try to call that, but I might just say avoid these problems. So yeah, any questions about any of that before we get going? All right, so completely switching gears from what we were doing the last few days of class, exponential growth and decay. Now we're going to talk about graphing for a bit. So before we get started, let's briefly talk about function notation. So often, as you probably noticed, I have used function notation already many times. We're at f of x or f of t or y of t. It's pretty typical notation. But often instead of writing y in the equation, we write f of x, meaning that the value of y depends on or is a function of the value of x. It's also just convenient notation to use. For example, if I'm writing some function like y equal to x minus 2 squared plus 3, and I want to find what y is equal to when x is equal to 4. If I actually want to write that out, I have to write something like, okay, I'm going to let x equal 4, then I'm going to get y equal to 4 minus 2 squared plus 3, which is 2 squared plus 3, which is 4 plus 3, which is 7. And it's kind of like, it's not the most compact notation. Whereas if instead I write my function f of x is equal to x minus 2 squared plus 3, then I can just say, oh, well, if I plug in 4, f of 4 is 4 minus 2 squared plus 3, which is equal to 7. And it's just a little bit more nice to say, well, look at this. If I write f of 4 equals 7, that means exactly when x is 4, y is 7. You're kind of containing all of that information in a more compact way of writing. So that's often why we like the function notation, because it's just an easier way of writing all the information down in one kind of quick step. That said, we often still use y, we often use f of x. We kind of go back and forth. People use them very interchangeably. The people are going to say y equals something, they're going to say f of x equals something, they're going to be in the same thing. So just you want to get used to hearing that. So we've already talked so far about how to graph lines, how to graph circles, how to graph parabolas. Now we're going to learn a few more graphs, specifically the square root function. So y equals to the square root of x, we are going to, I usually just like to start with plotting some points. And the easiest points are nice square numbers. So I'm going to pick x equal to 1. And y is going to be the square root of 1, which is 1. Oh, I should have started with what? What's even needed? Smaller number I can take the square root of. Right. If I plug in 0, the square root of 0 is going to be 0. Seems like whatever you plug in, you get out. That's not really true. If you plug in 4, the square root of 4 is going to be positive 2. And if you plug in 9, the square root of 9 is going to be positive 3. And I should point out, we're kind of cherry picking the nicest values possible, but you could totally plug in other values as well. Right? You could plug in something like 3 and get the square root of 3, which is approximately 1.73. But the point is, we're just going to kind of pick some nice, easy points to plot and then fill in the rest of the graph. So plotting these points on my very tiny XY coordinate system here. I got 0, 0, I got 1, 1, I got 4, 2, and I got 9, 3. And it's going to look like this. It does keep getting larger and larger and larger as you go to the right, or higher and higher and higher as you go to the right. And what I often say is that it looks like, and actually is, kind of half of a parabola turned on its side. So it's kind of like half of y equals x squared just turned on its side. And it really is actually not just like that, it really is that. A couple other things to talk about here, the domain of this function. So the domain is all the values of x that are allowed. The domain we should always think of as all possible x values. And in this case, x can be a non-negative number. So we can say that x is greater than or equal to 0, or using the interval notation, x starts as low as 0, it goes all the way to as big as you want. And interestingly here, the range is the same. The lowest y value you can get is, I should actually say, the range is all the possible y values. The range is all possible y values. And we get the same thing as the domain here. So here, if you look at the y values, well, the lowest y value you get is 0. And if you just keep going up and up and up, you can go up as high as you want. Now you have to go way, way out far to get high, but that's okay. Our range is going to be all y values greater than or equal to 0, or also written in interval notation the exact same way. Bracket 0 all the way to infinity and beyond. So, square root function looks like this, up and to the right. It never levels out, right? There's no horizontal aspect. It just keeps going up and up and up and up and up. And so I try and draw it that way so it looks like it's still getting higher. Okay, let's look at the next one. So what we're doing right now is we're talking about some parent functions, because what we're about to do with them is we're going to shift them or stretch them, or we're not going to stretch them actually, or reflect them is the other thing we're going to do. So absolute value function, great. It looks like just whatever x is, but positive if it was negative. So for example, if we plug in 0, the absolute value of 0 is 0. And if we plug in 1, the absolute value of 1 is 1. If we plug in 2, whoops, I don't want to plug in 12, I want to plug in 2. Try and take the absolute value of it. The absolute value of 2 is just 2. So if x is already positive, you just get out the same value. So you get plug in 0, 1, 2, 3, 4, etc. On the other side of things, if x is negative, the absolute value of -1 is positive 1. The absolute value of -2 is positive 2. Often when people describe what the absolute value of thing is, they really just say, people like to say it's how far away the number is from 0. So -2 is 2 away from 0. So the absolute value is positive. We always measure distance as a positive thing. So plugging these in, I get -1, 1, -2, 2, etc., -3, 3. You could go on forever. I'm just going to plot a few at this point. So it looks like this. People often say it looks like the letter V, although my V's typically look a little narrower than that, but it's kind of like the letter V. Yeah, we'll come back around to that. Here, our domain is everything. There is no x value that is not allowed. So I would say the domain is, you can either add with the words all real numbers. People often use the -infinity to infinity interval. The range, on the other hand, is the same as it was in the previous function. The range, the lowest y value is still 0, just like in the square root function. So our range is actually bracket 0 to infinity. Okay. Square root function, the absolute value function. And we're going to talk, there's something I really want to say about the absolute value function. We'll get back to that when we talk about piecewise functions a little bit later on. But there's kind of a nice way of thinking about the absolute value function. We've got one more function we want to have in kind of our catalog of functions that we're able to then kind of mess with, move back. So the last one, which is one that I'm terrible at drawing, is the cubic function. Y equal to x cubed. So let's plot some points. I'm going to plot a few points. They're not my favorite. So x is 0, 0 cubed is 0 times 0 times 0. If x is 1, 1 cubed is 1 times 1 times 1. If x is 2, 2 cubed is 2 times 2 times 2, which is 8. And so we can go negative as well. If x is -1, y is going to be -1 cubed, which is -1 times -1 times -1, which is -1. And -2 cubed is going to be -8. All right, so this one's hard for me to graph because it's always a super it gets big so fast. But we'll do our best. We got the point 0, 0, 1, 1, and 2, 8. and the point -1, -1, and the point -2, -8. The very skinny looking graph here. All right, I'm always like, I really don't like drawing this. It never looks good. So look kind of like this. We come up, try and hit that point. We go through the origin. That's not terrible. It could look better, but it's domain. Is there anything X is not allowed to be here? No, we're good, right? So I will point out now and later, when we talk more about domain, typically when you're thinking about the domain of a function, you're going to kind of think X is not allowed to be. Usually you only run into problems if you have like maybe division by 0 or a square root of a negative or a logarithm. Because none of those things are showing up here, we're not too concerned about domain. Or we're really not too concerned that X is going to be anything that's not allowed. So here our domain, again, is everything. All real numbers from -infinity to infinity. And here the range is also everything, right? That function has super duper low y values and super high y values. So our range is also every darn thing. So maybe not new functions, but 3 functions to add to our list of functions we can graph very not too terribly. I will point out, usually when I'm graphing these, I am not super precise about them. So like if I was actually going to graph these on my own without being too precise, I would be like, okay, here's my square root function. And if I was graphing it, I would be like, okay, it looks like this. Great. Maybe I plot a point here. Maybe I plot a point here. But I'm not trying to be super duper precise. Similarly, if I was graphing the absolute value function and trying to just kind of get a brief idea of it, I would just be like, okay, there's my function. Same thing for the cubic function, especially because I hate drawing it so much. If I was doing my cubic function without like grid lines there, I'd be like, okay, well, it looks kind of like this. And it goes to the point 1, 1. And right, it doesn't look great, but it's informative enough that someone's like, well, yeah, he knows what he's talking about. The graph is good enough. So your graphs don't have to be perfect. They just have to look like you have an idea of what the thing is supposed to actually look like. Okay, so, but of course, I'm trying to show you how things look. So I'm trying to be somewhat precise. A couple things about transformations of graphs. So we're going to talk today about how we can reflect graphs and how we can shift them. So first of all, the reflections. And I'm going to say actually a very kind of general statement first. If you have something happening outside of the function, it's going to affect the graph in a vertical way. Whether it's putting a negative outside or adding something outside or multiplying by something on the outside, it affects the graph vertically. Whereas if something happens on the inside of the function, it's going to affect the graph horizontally, whether it's multiplying by a negative on the inside or adding something on the inside or multiplying by something. So let's look at a brief example here. My favorite example of this is if your original function was f of x equal to x squared, which is everyone's favorite upward opening parabola. It just looks like this. I'm not even going to draw an xy coordinate system. Like there's your f of x equal to x squared. Then y equal to negative f of x would be y equal to negative x squared, which is a downward opening parabola. So the idea there is, oh, that negative on the outside is just flipping it over vertically. On the other hand, this one's harder to come. I could come up with that example, but we've got that one later. So if your function has a negative on the inside, it's kind of like you're doing the negative first. So here's an example of that. Let's say our function was f of x equal to the line x plus 2. To the straight line. Not a good example, James? Yeah, it's a fine example. Sorry, I was thinking about something else. So this line has a y-intercept of 2, x-intercept of -2, looks vaguely like this. Label my points there. Whereas if I put the negative on the inside, check this out. Y equal to f of negative x is going to be negative x plus 2. it's going to have the same y-intercept, but now it's going to be a downward line from left to right. So it's going to look like I reflected it in the y-axis. So that now it's going down from left to right. Like that. And that's sorry, that one doesn't look super great, but hopefully you get the idea there. So a negative on the inside of the function is going to reflect horizontally. Whereas a negative outside of the function is going to reflect vertically. And these are kind of the two graphs I keep in mind when I'm thinking about what's happening. But let's look at a couple other examples of graphs we just learned about. Bless you. Sorry, that was kind of loud. Bless you. Very, very aggressive bless you. So if we want to graph f of x equal to the negative absolute value of x, that negative is on the outside. So we're thinking of taking our V-shaped graph and just flipping it over the x-axis. So it's going to be a downward opening instead of an upward opening. Now, if you're not sure what's going to happen, one way you can kind of test things out is just to plot a point or two. So for example, if x were to be 1, y is going to be the negative absolute value of 1. Absolute value of 1 is 1, so I get a negative 1. So we do the point 1, negative 1. Similarly, if I plug in 2, I'm going to get negative 2 for my y value. Every x value that's positive is going to give me out a negative y value. So I'm at least sure I'm going down, down, down this way. But also the same thing's going to happen if I pick negative values for x. If I plug in negative 3 for x, the absolute value of negative 3 is 3, and then you have a negative of that. So you're still getting negative 3. So if I plugged in negative 3, I would also get negative 3. So we're going down that way as well. We're just taking that previous absolute value function and flipping it over the x-axis because there's a negative on the outside. Just to point out something else, if the negative were on the inside, it wouldn't actually change the function, how the function looked at all, right? If you put the negative on the inside, it would flip it horizontally and it would still look the same. It would not be very exciting. Okay. Square root of negative x is going to take our usual square root function, which goes that way, and it's going to reflect it across the y-axis, so then it should go that way. Let's plot a couple points though, just to be sure. So interestingly here, you can't pick x equal to 1 or 4 or 9, because if I pick x equal to 9, I'm going to have the square root of negative 9, which is imaginary. And we don't graph imaginary numbers on the real coordinate system. So we don't want imaginary results. We want real results. So we have to pick values for x that give you positive inputs there. So we need to pick something like x equal to 0. Because the square root of negative 0 is still the square root of 0, which is just 0. Or if we pick x equal to negative 1, you get the square root of negative negative 1, which is just 1. Sorry, that looks terrible. Or if you pick something like negative 4, you get the square root of negative negative 4, which is just 2. So we're having to pick negative values for x so that we take the negative of those, which become positive, and then we can take the square root of positive. So we're really just getting this original square root graph reflected over because the x value has to be negative instead of positive. So we've got a 0, 0 still, and a negative 1, 1, negative 4, 2, and we would get a negative 9, comma positive 3. It's going to look like the same graph reflected over the y-axis. Okay, so reflections, that's kind of how they work. You have a negative outside, it reflects it vertically. You have a negative inside, it reflects it horizontally. The other thing, so the last kind of thing we do, which we're not doing today, is the stretching. And the stretching is kind of weird. Like the stretching is something people often kind of just gloss over. But the two kind of transformations you should be more aware of when you're graphing things are reflections like this, and then shifting like we'll see on the next page. So So what does adding a number do to the graph of f of x? Well, we can add it outside or inside. Adding it outside is going to shift the graph vertically. So this shifts the graph vertically. And it's going to shift it up if d is positive or down if d is negative. So it's going to shift it up if d is greater than 0. It's going to shift it down if d is less than 0. Think about like your x squared graph. So in fact, let's give ourselves some space up here. For example, if I was going to graph something like y equal to x squared plus 3, that's just shifting your usual x squared graph up 1, 2, 3 places. So instead of having a vertex at 0, 0, your vertex would be at 0, 3. That would be a shift up. If it was x squared minus 3, it would shift it down by 3. So when you add outside of the function, it's going to shift it up or down. On the other hand, if you add a number inside the function, and this is where things are a little bit interesting, it's going to shift the graph horizontally. And the thing that people always kind of feel like about with the horizontal shifts is they kind of feel counterintuitive. So if you add a number inside the function, it's going to shift it to the left. And if you subtract a number inside the function, it's going to shift it to the right. And I'll tell you how I like to think of it, but let me write down the thing first. So it's going to shift it. Let me try to write the right thing. It's going to shift it left if C is positive, and it's going to shift it right if C is negative. So here's what I like to think of. Let's go ahead and look at the example up here for a second. Let's say we want to graph y equal to x minus 2 quantity squared. So usually, if I was graphing just y equals x squared, my vertex would be at the origin. X is 0, y is 0. So now here's how I think about this. I'm going to shift this 2 to the right. And the reason I have to shift the 2 to the right is because x needs to be 2 larger than it would have been to still get the same y value back. So previously, if you're comparing this to y equals x squared, x needs to be 0 for y to be 0. This one, for y equals x minus 2 squared, x has to be 2 for y to be 0, because 2 minus 2 is 0, and 0 squared is 0. So I want to say it again, x has to be 2 larger than it would have been to get the same y values back. That's why we have to shift 2 to the right. On the other hand, if we were graphing y equals x plus 3 squared, we'd have to shift 3 to the left, because x needs to be 3 less than it would have been to get the same y values out. So that's why the shift maybe seems slightly counterintuitive. When you're subtracting, you're shifting right, because x needs to be larger to overcome the subtraction you're doing. Or if you're adding on the inside, x needs to be smaller than it would have been to overcome the addition you're giving. So this graph here would look like shifting that vertex 2 over to the right. Something like this. That's why subtracting on the inside is a shift to the right, adding on the inside is a shift to the left. Okay, so now we've got some of everything over here. So here's the thought process for graphing something like f of x equal to the square root of x plus 1 plus 4. I'm going to think about how the original graph looks, right? My parent graph, and let's see, yeah. This is where like the graphing gets kind of messy. I bring my pencil. Let me look for my pencil real quick. Drawing pencil is erasable, whereas, yeah, cool, pencil, all right, good. So I'm going to start with my parent graph, y equal to the square root of x. It looks something like this. There's my parent. And then I'm going to think about how this graph is going to get shifted. So the plus 1 is going to shift it 1 to the left, and the plus 4 is going to shift it 4 which way? Up or down? You can point, yeah, point up or down. Well, I don't want to point. I know pointing's kind of rude, but you're not pointing at me, so it's okay. Yeah, okay, good. Yeah, so we're gonna go 1 to the left and 4 up. So what I really like to think about is just where kind of I kind of think about graphs having like important points, meaning like for the square root graph, where it starts is kind of like the vital most important point. So I'm thinking of where 0, 0 is actually going to move to. So that 0, 0 point is going to go 1 left and 4 up. My graph is now starting here at the point -1, 4. See a little bit better here. So but then it's just going to look like this, just starting here. So I'm going to go up to the point 0, 5, and I should find the point 0, 5 because I should find any intercept I'm going to have. So I know if I set x equal to 0, square root of 1 is 1, 1 plus 4 is 5. I get the point 0, 5, and then it just keeps on going. It looks like I just moved that graph over 1 to the left and 4 up. Now you can also plot more points if you want it to look more precise. I obviously didn't. I was trying very, very hard not to be like, okay, well, where does this point go? So you don't have to be super duper extra careful, but you should definitely make note of the y-intercept here, which is the point 0, 5. Oh, I should move that cursor out of the way. All right. So same deal over here. This one's going to look less good because it's mainly graph, but we're taking our parent graph of y equals x cubed. Try and draw not too terribly here real quick. Like here's y equals x cubed. It does really flatten out at the origin. I'm not the best at drawing. Ooh, yeah, okay. Good job, James. All right. So there's your y equals x cubed, and we're shifting it 5 to the which way? To the right. And 2. So what I'm thinking about is where my origin points. I do have a point at the origin. I'm thinking about where that's going to end up first. So I'm going to shift that 5 to the right and 2 down. So that's kind of my new origin, for lack of a better word. And then I know the graph goes over 1 and up 1. So I'm going to plot this point here. And it also goes over 1 and down 1. So I'm going to kind of plot those 3 points. Now it's not a straight line. I know I've got 3 lines that are kind of, or sorry, 3 points that could make a straight line, but it's not. It's just going to have the same shape. So it's going to look, ooh, all right. Good, wish me luck. This one's always a challenge. Okay, come on, we can do it. Come on, we can do it. Oh, wow, that looks not the best, but it's good enough. So learn from me in that your graphs don't have to be perfect. As you can obviously tell, it is not perfect. But I do care about this point here. That point is the point 5, -2. And I will point out there are some intercepts here that we're not going to worry about. I know I said we usually find the intercepts. It depends. So here you could totally find the x-intercept. It's gross. It's the cube root of 2 plus 5. I don't think that's really what we need to be doing. It's not the point of these questions. I will also say somewhere way down here, you can't see that, way down here is the y-intercept. If you set x equal to 0, you would get a value for y. It would be -125 minus 2. We're not going to worry about that. So if the intercepts seem reasonable to find, it's a good idea to find them. If they don't, then they don't. Okay, let's look at these next two. We've got negative absolute value of x minus 2. So this has a shift and a reflection. And we'll talk about the order you want to do things in a second. Here, you always want to kind of work from the inside out. So here I see inside the absolute value. I'm subtracting 2, and I'm shifting 2 to the right. So that's telling me to go 2 to the right. And then this negative sign out in front here is telling me to do a which kind of flip? Is it outside the function or inside the function? Right, it's outside. So that means it's going to have to be which kind of thing? Vertical or horizontal? Vertical. If it's outside the function, it is vertical. If it is inside the function, it's horizontal. And when I say outside or inside, I kind of mean like, so the way I'm saying, the reason I am saying this is on the inside here is because I'm doing x minus 2. And then after that, taking the absolute value. And then after that, doing the minus sign. So the 2 is getting subtracted before I kind of quote unquote do the function. And then the minus sign is happening after I have done the function part, where the function is the absolute value part. So that's kind of how I'm looking. Same deal here, right? For this one, I do x minus 5, then I cube it, which is kind of the parent function part. And then after that, I subtract 2, which is why the 5 on the inside is shifting us horizontally, and the 2 on the outside is shifting us vertically. That's really how I am wanting you to look at these things. Okay, so oh, by the way, make sure everyone on Zoom got the attendance form while I'm thinking of it. There's it again, in case you need it. So we're going to go 2 to the right. So we're going to end up not at 0, 0, but I guess I could start with my parent graph. Okay, here's my parent graph. You don't have to draw the parent graph. I kind of like to, just to kind of see where things are, but you probably don't want to draw the parent graph generally if you don't need to. So we're going 2 to the right, and then instead of doing an upward V, we're going to flip it over and do a downward V. Not too terrible. All right. Another square root. So taking our parent graph, which is this one here. And the negative inside is going to flip us. That's a horizontal flip. So I meant to write on the previous one, that was a vertical flip, sorry. So this one's going to be a horizontal flip. And then we're going to go up 3. So it's going to be going, flip it over. And it's kind of, you can't really like show you, like I'm flipping it over, right? And then I'm like, I wish I could just, I need like another like clear piece of paper. I just like, that's a good idea. Next time I do this, I should get like a clear graph I can put on top of it and just literally flip it over. Brilliant. I'll remember it. Okay, maybe. So remind me if I ask you next time, like, what was the cool thing I said? You guys will remind me. I mean, cool. Flip it over and then shift it up 3. So it's going to be opening to the left, and then it's going to go up 3. So my starting point is going to be 0, 3. And then instead of going to the right, it's going to go to the left. I'm never good at as good at drawing it to the left as I am to the right. I don't know why. It's not much practice, I guess. So there's your okay looking horizontal flip. And then 3. It looks, I'm not super proud of this drawing. I'm gonna say it looks like it flattens out a little too much, in my opinion, right? It's looking a little too flat. It should be having more of an upward kind of direction there, like that. Again, try your best, right? Sometimes the graphs, as you can tell with this one, are gonna look like garbage because sometimes you just don't do a good job. Yeah, graphing is always a mixed bag because things can just, it is partly based on your ability to draw things well. And some people are better drawers than other people. And yes, practice does make it better, but I've had many years of practice and my graphs are still just adequate, I would say. So do your best, practice. If things don't look absolutely perfect, it's not the end of the world. Okay. So there's a couple things to know specifically when you have 2 horizontal things going on or 2 vertical things going on. So horizontally, and this is kind of weird. It's taking me a long time personally to get this correct. Horizontally, you want to shift before you flip. Vertically, you want to flip before you shift, which is kind of annoying that it's not the same. Right? It would be lovely if they're both do one thing, then do the other thing, but they're not. They're opposites of each other. So here's what I mean. So for this graph here, if I want to graph y equal to the square root of negative x plus 2, I'm going to shift first, which may feel counterintuitive. But this plus 2, that's going to shift me 2 to the left. That's going to shift me 2 left. And then this negative here is going to give me a horizontal flip. And let's go ahead and graph kind of all the little in-between parts here so we can kind of see what we're going to get here. Yeah, that's fine. So here's my parent graph, good old square root. get a little square, yeah. Now, first, we're going to go 2 to the left. I'm just going to move over 1, 2. And then it's going to have, the point, that point there, and the point there. So it's going to look kind of like this. And then we're going to shift it. Sorry, we're going to flip it over. So now here's where the interesting part happens. When this shifted graph flips over, this point -2, 0 is going to flip over the y-axis to the point +2, 0. It's going to end up over here. And just for some more context, this point -1, 1 is going to flip over and become the point +1, 1. And then this point that I graphed, which was 2, 2, is going to flip over and become the point -2, 2. I'm getting all of these points that look like this. Let me graph myself a little more. I'm also going to do the point -7, 3. So it's going to look like this. But it really, really is the case that you want to do the shift first and then the flip of that shift. One thing I like to think about, especially for square roots, is you can also kind of figure out how things are supposed to look based on what the domain is going to be. So x can only be as big as 2. If you pick a value of x that's too big, look what happens. Let's say we picked x equal to 3. Then y is going to be the square root of -3 plus 2. But that's the square root of -1, and we don't want imaginary numbers. So we know that 3 is too big. Out of bounds. On the other hand, 2 is perfectly fine. Plug in 2, you get the square root of -2 plus 2, which is the square root of 0, which is just 0. So 2 is the upper bound for the domain. In fact, you could totally find the domain by saying all that stuff we're taking the square root of had better be greater than or equal to 0. And then if you add x to both sides, you get 2 is bigger than or equal to x. Or if you prefer, x is less than or equal to 2. Oh, x has to be less than or equal to 2, which totally corresponds to how this graph looks. X is definitely less than or equal to 2. So again, when we're doing things horizontally, we shift first, flip second. I used to try and flip first, but then things would be weird because you'd have to like flip first and then kind of shift the opposite direction you really felt like you should be shifting. So if you have another way that works for you, that is totally fine. This is the way I've been able to boil it down for myself that like, okay, I can make sense of this. Shift first, flip second. And then for the other one, we do the opposite. So if we've got vertical things instead, where we're flipping and shifting vertically, we're going to flip first and shift second. Here's why. So just to kind of point out here, this graph here, negative absolute value of x plus 3, if I were to shift first and say go up 3, kind of terrible, I should use a piece of paper here. So just to kind of show why we don't want to shift first, if I shift first and go up 3, so there's my absolute value of x plus 3. And then if I were to flip that over the x-axis, it's going to flip in a way where it looks like this. So this flips all the way over so that that point comes down there. So it's going to be looking like that. And that is not y equal to the negative absolute value of x plus 3. It's equal to the negative of the absolute value of x plus 3, which is a totally different thing than negative absolute value of x plus 3. So we're not going to shift first and flip second. We're going to flip first and shift and shift second. So parent graph. And then our flipped graph. So sure, I'm going to draw in a different color. So here's our parent, y equal to the absolute value of x. Here's our flipped graph in red. Y equal to the negative absolute value of x. And finally, our last final result, we're going to shift this up 3. We're going to get 1, 2, 3. So we're just moving that up 3, and we're going to get this final actual graph. Now, if you were graphing this on your own, you probably don't want to have all these graphs on your graph. You certainly, it's fine if you want to draw them. Just make sure you indicate what graph is actually the final thing you're trying to draw. So here in blue is our y equal to negative absolute value of x plus 3. Just to say a couple of things here. This was a 3 up. That was a vertical split. And you could, right, again, if it's not super duper immediately clear, like what's going to happen, it's always totally fine to plot some points. We try to move away from that because plotting points is a time-consuming process, and we want to kind of graph things and know what they look like without plotting points. But it's still a perfectly fine thing to do. So, like, if I was going to say I want to plot some points, if x is 0, negative absolute value of 0 plus 3 is 3. If x was 1, the negative absolute value of 1 plus 3 is just negative 1 plus 3, which is 2, and so on. If x is 3, the negative absolute value of 3 plus 3 is negative 3 plus 3, which is 0. So I'm getting the points 0, 3, and 1, 2, and 3, 0. If I plug in some negative numbers like negative 2, the negative absolute value of negative 2 plus 3 is, you always have to deal with the absolute value part first. So that negative sign can't just hit that negative 2. You have to say, okay, absolute value of negative 2 is 2. So that's going to be negative 2 plus 3, and then negative 2 plus 3 is positive 1. So when x is negative 2, y is positive. So it's totally fine to plot points. It's just not absolutely necessary. So 3 new graphs, or 3 graphs to add to our catalog, whether or not they're new. The square root graph, the absolute value graph, and the cubic. And then another couple at the end here, which we're not going to transform so much as just look at. If I can find the paper I'm looking for, maybe someday. Yes, here we go. So 2 more graphs. They're kind of important. There's some rational functions. So what is a rational function? So just, everyone's aware, rational function is just a polynomial divided by another polynomial. I can spell it. That's what a rational function is. Polynomial on top, polynomial on the bottom. And a polynomial is just a function where you have non-negative integer powers of x. So like x squared plus 3x plus 5, or 2x minus 1. Right? Parabolas are polynomials, linear functions are polynomials, cubic functions are polynomials. Anything where you have nice non-negative powers of x that aren't fractions, right? That are integers. And even unexciting things like 1, which is a constant, that's technically a polynomial as well. And so is x. They're just not very exciting polynomials. So this is totally a rational function because you have a polynomial on top and a polynomial on the bottom. And let's see what happens if we pick some values for x. So let's say, well, let's pick some easy values like 1. If x is 1, y is 1 over 1, which is 1. If x is 2, y is 1 over 2, which is 1 over 2, or 1/2. And if, let's go big for a second, if x is 10, y is going to be 1/10. And if x is 1,000,000, x is going to be really, 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 really small. So the thing we actually kind of care most about with this function isn't so much that it's a rational function. It's that if x gets very, very large, the y values get extremely close to 0. They never actually get to 0. You can't actually make this function equal 0, but it's going to get super duper close to 0. So we start at the point 1, 1, and then the point 2, 1/2. This graph just gets very small very fast, and it has a horizontal asymptote at y equals 0. That's just part of the graph, though. It's certainly not the whole thing. If we let the values of x get closer to 0, like if we pick maybe 1/10, what's 1 divided by 1/10? 10, right? Because when you divide by a fraction, you flip and multiply, and 1 times 10 is 10. Or if x was even closer to 0, like 1/1000th, 1 divided by 1/1000th is going to be 1,000. This is actually a really important thing that comes up again and again and again, which is that in a fraction, if your denominator is large, your overall value is small. And on the flip side, if your denominator is small, your overall value is large. This is an important thing, definitely going to come up in calculus a lot. So as x gets very, very, very close to 0, the y values get very, very large, like that. And we have a vertical asymptote at x equals to 0. Now, this is only half the graph. The other half is when x is negative, the same sort of thing happens. So if x was a negative large number, like -1,000 or -1,000,000, your y values would be very, 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 very small as well, but they would be negative. So you'd be really, really close to the x-axis, but like over here. And if x is really, really close to 0, like maybe -1/1000, then the y value is going to be 1 over -1/1000, which is -1,000. So if x is really, really, really close to 0, but negative, the y values are super duper big, but they're super duper negatively big. In fact, I would encourage you to use that language when you think about this. I would say that as x gets very, very close to 0, the y values get very, very large. And as x gets very, very close to 0 from this side, the y values get very, very, I wouldn't say small, I'd say the y values get very, very negative. Because that's the way we want it. Am I missing anything here? I don't think so. Let me double check. Nope, we're good to go. Okay. And then finally, this last one, which I've kind of like taken over here. Sorry, I feel like I've done you a disservice last function here. Y equals 1 over x squared has a lot of the same behaviors. If x gets big, 1 over x squared is going to be super duper small. If x gets very, very close to 0, 1 over a very, very small number is going to be very, very big. But the difference here between this one and the previous one is the previous graph, if x is positive, y is positive. If x is negative, y is negative. Where here, if x is positive, y is still going to be positive. If x is negative, y is still going to be positive. We're going to be squaring that number. So I'm going to plot a couple points like if x is 1, y is 1. If x is -1, y is 1 over -1 squared, which is still 1. If x is big, like 10, y is going to be small. And if x is negatively big, like -10, y is still going to be positively small. So we're going to be looking something like this. Oops, because you don't want to cross the x-axis like that, James. Sorry. So that's what's happening as you go way out to the other side. X is big, y is small. If x is negatively big, y is small. But then as we go towards the middle, when x is really, really tiny, and if x is like 1 over 10, y is going to be 1 over 1/10 squared, which is 1 over 1/100th, which is 100. Or if x is -1/10, y is going to be 1 over -1/10 squared, which is still 1 over positive 1/100th, which is 100. So as x gets really, really close to 0 from either side, the y values still get very, very large. And so just like the previous graph, we would say this graph also has a horizontal asymptote at y equals 0, and has a vertical asymptote at x equals 0. So those are some new functions that maybe you have seen before, maybe you've not seen before. We have 5 new graphs. Square root of x, absolute value of x to the third, 1 over x, 1 over x squared. And the idea is that we can use our flips and our shifts to kind of graph all sorts of things.